All right, guys, welcome to Nitrox. I'll be your instructor this evening. My name is Benjamin Hadfield, and I'm a technical diving instructor certified all the way through advanced Nitrox in terms of as being an instructor. What that means to you is I can teach this class all the way through. I can teach you how to use all the way to 100% Nitrox, or which would be pure oxygen. Let's see, I'm going to go to share my screen. Take me just a second. Share. And why isn't it sharing? Take me just a second. We've had some weird issues today, that's for sure. We had a wonderful conversation with Sparklight today. There we go. All right, now we're sharing our screen. So there we go. Can you guys all see my screen? Fantastic. And I'll make that a little bit larger as well. So, and what I was telling you is I'm also assistant instructor trainer and teach Nitrox as well as all the way through 100% oxygen as well. Now, as you guys go through this class, I always ask my students to do one thing for me, and that's to think about where you want to take your diving adventures to and what that looks like to you to make sure that you're getting as much out of my classes as possible so we can tailor them to the direction you want to go. Now, as you kind of think about it, obviously we have the easy answer that I want to go somewhere and see pretty fish, but maybe think about it a little more deeply. Do you want to see wrecks? Do you want us to do something deep? Do you want to dive high elevation? Do you want to do ice? Do you want to see things that come out at night? Those are all considerations for diving to think about. So as you kind of go through this process, think about what you'd like to see and where you'd like to go and what that looks like to you. We're happy to help you find that journey. Another class I encourage strongly is going to be React Right and Stress and Rescue. Now, the basic courses I suggest are pretty straightforward. I always suggest deep and night and limited viz because cool things are deeper than 60 feet and cool things, different things come out at night as well. So as you kind of look through that process, those are two that I always suggest, and then Stress and Rescue with React Right to make sure that you are a safer diver as well. So let's kind of jump into the meat and potatoes of it. What is Nitrox? Who's got that for me?
The higher oxygen concentration.
That is exactly right. Higher than what, though?
Than the traditional compressed air tank.
Perfect.
Yeah.
Traditional air. What are we breathing right now, though? It's what is it?
71% nitrogen, 29% oxygen.
That is correct. Absolutely. So Nitrox would be technically a blend of anything over 21%. So, but really, truthfully, if you really look at the true definition, Nitrox is any blend of gas that is oxygen and nitrogen. But for the purposes of our diving journey for this evening, we're going to call it anything over 21%. So as we breathe, the gas that we're surrounded by is 79% nitrogen, is exactly what you said, and it is 21% oxygen. Now, the precluding factor, the challenge with most diving is the nitrogen that we're breathing. As the nitrogen comes in our system, it's not a bondable chemical. It doesn't, like oxygen, carbon dioxide, and carbon monoxide all bond to the hemoglobin in our bloodstream, right? Whereas nitrogen doesn't. Nitrogen is a free flow, and it flows into our bloodstream and into our tissue. And our tissue compartments, like our fat, our blood, our fat, our bones, our muscles, the nitrogen gets lodged into those tissues at the partial pressure we're dealing with. And so as it gets lodged in there, it has to also be able to come back out. So nitrogen becomes one of the main precluding factors to diving that cause our dives to be shorter or less safe, because it's the nitrogen that causes the bends like DCS. So the nice thing with Nitrox is, for example, if we were breathing a 32% blend of Nitrox, we're breathing less nitrogen. And the easiest way to think about that is, if I don't drink any beer the night before, can I have a hangover?
No.
No, absolutely. So if I drink less beer, I have less hangover, right?
Yep.
Same thing with nitrogen. If I breathe less nitrogen, I reduce my potential chances of having issues. And the higher the percentage of nitrox I breathe, the less chance I have of having a problem with nitrogen problems. So there is also limits to that as well. But as we talk about that, what we're going to delve into is we're going to get you certified in Nitrox levels 1 and level 2. Now, if you did your homework, you'll notice that nitrox level 1 is 32%. What is nitrox level 2?
36.
Close.
40%, right?
40% is exactly right. Now,
Oh, I see.
Now, that number is extremely important because we're going to talk later on about what the Rule 40 is. And it's going to deal exactly with that idea that there is limitations to nitrox with equipment, and it's based upon that magic 40% that we just talked about. So that's what we're going to be working on as well. So there's using nitrox, and some of the advantages to diving nitrox are pretty simple. And we've talked about that in class. What are some of those advantages?
You're going to have longer decompression limits where you can dive longer without having those decompression times, and then you'll be able to be safer.
That's exactly. So it's not so much deeper, but deeper without issues. And so that's kind of a little of the fallacy is, can you dive deeper? Sort of yes, no, not really. We'll get into that a little bit more deeply, but absolutely one of the advantages of diving nitrox is it gives you more bottom time, shorter surface intervals, and more energy after the dive. Now let's talk about those in turn. So if we start talking about the idea that we've got more bottom time and less surface intervals, what that means is we're taking up less nitrogen, and the nitrogen again is the precluding factor. So we know that if we go to a party, and I'm going to use the beer analogy a lot because it pretty direct translation. So the idea is if I go to a party and I only have one beer and then I wait an hour, I can drive, right?
Mm-hmm.
Fair enough. I mean, I think that's the standard, right? And that's the idea. So if I breathe less nitrogen, I'm good to go faster. I have less issues later on, right? I don't have to have as much surface interval because now I'm ready to go diving again. If I drink 12 beers, lots of nitrogen, then I have to wait a long time before I can drive, right?
Mm-hmm.
Yeah.
And the same thing with nitrogen. So the more nitrogen I uptake, the bigger the problems I have. So one of the big advantages of nitrox is because I'm breathing less nitrogen, I've got the ability to stay down longer because I'm drinking less beer, if you will. I'm uptaking less of the problematic chemical. So, and with that, because I've been good and I breathe less nitrogen, I don't have to have as long a surface interval to get rid of the nitrogen as well. Now, one of the things that happens is as this nitrogen is going through our system and going into our tissues, our bone, our brain, our muscles, our fat. Raw, you don't have that, but some old guys like us have fat, right? And I have to deal with that, but you don't. It's all good to go. So, but old guys like me, and you with your bones and your muscles and everything, we absorb this nitrogen and then we expel the nitrogen. So think about it like this: the more nitrogen I intake and the more nitrogen I have to exhale through the process of the ascent or the descent, right? That causes my muscles and my body to have to work, right?
Mm-hmm.
So which is easier? If I go for a 5-mile walk gently, or I go for a 5-mile fast run, which is easier?
5-mile walk.
Absolutely. So the oxygen in this case, the nitrox is going to make our body work less. So if we work less, we have more energy after our dive, right?
Yes.
Absolutely. Now there is a little debate in here. Does oxygen have a narcotic effect? What do you think?
Medically speaking, if you turn it up high enough, yes, it does have a slight narcotic effect.
Yeah, absolutely. So you're breathing, and the nice thing is a partial pressure. You'll be breathing at that level. So it's got a slight narcotic effect. And necessarily you get a little bit of buzz after a dive as well because of that. But mostly it's because you haven't worked out as hard. You had an easier dive. Now, nitrox absolutely has limitations as well as we go. So what are some of the limitations we have for nitrox?
So as I was reading, it's like you can't go past certain depths with the nitrox when it's at a high concentration, because then that subjects you to and my English failed me, but it subjects you to Andrew.
Toxicity or pulmonary toxicity.
Yes,
Mm-hmm.
Thank you.
Absolutely.
I'm a fail.
Well, that's why I'm the instructor. I read this once or twice, so it's all good. So absolutely. So there is definitely a limit to the depths that you can go. What other limits are there to breathing nitrox?
Mm,
So we have the depth.
Maybe
uh-huh.
10 somehow.
Yeah,
I'm
well,
sorry, say that again.
concentration.
Concentration or like the time, like the limit would be.
Time. There you go. You got it, Andrew. Good job. So time, absolutely. So there are definitely clocks and charts about how long you can breathe nitrox for. Now, the good news is, and I just want to preface this whole course with it, is the amount of time you'd have to breathe nitrox to get to pulmonary oxygen toxicity or central nervous system toxicity is immense. And as a recreational diver, it will be extremely, I mean, you would have to work really, really, really hard past your ability to get into either of those. So the good news is this is a precursor to when you get into the more complicated stuff, but for you to get into those true limitations, it's going to be fairly difficult. Now, where you're going to get into the limitations is setting up the depth, but not so much time. So let's talk about the idea of partial pressure. I just happen to have some sponges. Much to my wife's great dismay, I went into the sponge drawer and I cut up some sponges. And so as we look at these, can you guys see me clearly enough?
Yeah.
So this is, I like this sponge because it really kind of demonstrates about the percentage of what we're breathing. If the dark blue was oxygen, the light blue would be nitrogen. All right. And as we look at this is about 1 inch by 1 inch by half an inch, right?
Mm-hmm.
So it takes up about 1/2 of a cubic inch, right? So that's what we're breathing on the surface. If this was one molecule of what we're breathing on the surface, when we get down to 33 feet, what we're doing is essentially taking 2 of those molecules and we're squeezing them together. So now we have the same 2 molecules occupying the same amount of space as they would at the surface. Does that make sense?
Mm-hmm.
Perfect. We get down to 66 feet. It's the same. We now have 3 of the same molecules occupying the same space as we would at the surface, as one of these would at the surface. So that's what we're literally doing is we're squeezing them down. We get the same amount of molecules in that same amount of space. And if we get to 99 feet, it's the same thing. We're squeezing 4 molecules into the same exact space. Now that's Henry's law for you to a certain degree. Or actually, I'm sorry, that's Dalton's law. And that of partial pressure. So as we squeeze that down, that's what's going on. So as we look at it, let's go back to sharing my screen here. Can you guys see my screen?
Yep.
Fantastic. So this is what we're looking at. At 1 ATR, 1 bar, for our Europeans among us, we're breathing 79% oxygen, 21% oxygen, 79% nitrogen, 21% oxygen. Now, as we get down to 2 bar, which is 33 feet, that's the same as squeezing those molecules together. It is the same as breathing 158% nitrogen and 42% oxygen. Does that make sense?
Mm-hmm.
Now, if we follow this same theory out of doubling out, multiplying, we got at 1 bar, 21%, 2 bars is 2 times 21%, gives us 42% oxygen. If we go down to 3 atmospheres, what is the partial pressure of oxygen, Ra?
63.
Exactly. Good job. And if 99 would be 4 times that, it'd be 84, right?
Mm-hmm.
So that's what's happening. We're breathing a higher partial pressure of oxygen. Now, as we get to that point, if breathing 100% oxygen can become slightly problematic, correct?
Yes.
Okay, good job. I'm glad I'm right on that one. Just want to make sure. I like to test myself once in a while just for fun. I don't know what happened to all my fonts, but for some reason, all my fonts went to really small, and so I'm having to correct that. So partial pressure of oxygen based upon the depth and the fractional of the oxygen and how we calculate that partial pressure is extremely important. Now, there's a couple pre-factors we want to talk about as we go into this. Can you guys see the red and blue screen?
Mm-hmm.
Perfect. So what we're
The
breathing
red and blue screen?
or red and white, I'm sorry.
No, it's still using nitrox, the advantages of nitrox.
Oh, let's fix that. I apologize. Let's see, share screen. My screen is not changing at the same time. hide. Take me a second to present. Let's see. All right, entire screen. There we go. Okay, so you should see now a red and white screen.
Mhm.
Fantastic. Now, as we look at this is a great description point. Right now, we are right here in the middle. Breathing 21% oxygen, a partial pressure of oxygen of 21% is the normal partial pressure level for air that we're breathing. So if we take that down into the negative, if we go to 16%, like that's the threshold for hypoxia. That's exercise tolerance and mental performance diminishes at this level. So think about it like this. If you were going way up in altitude where the partial pressure that at 0.16, that would be about 10,000 feet, roughly. It's actually 9,200 feet.
Yeah. Table
So
roll.
we get 9,200 feet. We try and go for a run. What happens, Raw?
You start gasping and then going and breathe 1, 2, 3.
Exactly. So that's the threshold for hypoxia, and you don't think as well, your performance is certainly diminished. Now, as we continue in that partial pressure, we reduce our partial pressure to 0.12. That's the minimum partial pressure required to maintain consciousness without passing out. Now, if you have your notepad available, I would write this one down. 0.10 is the minimum partial pressure level required to sustain life. Make sense? If you get into a situation where it's less than 10% oxygen, you will die. So, and dying is bad. So now on that opposite side of the case, as we start descending into partial pressure of oxygen increases, at 1.1 is the threshold where oxygen toxicity symptoms may occur. At 1.4, I would write this number down. 1.4 is the partial pressure at which oxygen presents a moderate risk to divers and recommended as the partial pressure limit for recreational divers. 1.4 is a very, very important number for you guys to tattoo on your wrist or on your forearm or your leg or wherever you'll remember to see it. 1.4 is a big number you will want to remember. So, Raw, if you want to write that on Andrew's forehead, so every time you get ready to do something, you just look at his forehead and you know that 1.4 is the right number. I'm sure he will absolutely let you do that, right?
Mm-hmm.
Does that sound good, Aaron or Andrew? I mean,
Yeah.
perfect. Okay, so if you need, I have a nice Sharpie. I'll be happy to bring to open water tomorrow, so you can make sure that that's written well. But as we continue up that scale, 1.6 is the other number I'd like you guys to write down, because at 1.6 partial pressure of oxygen is the level at which oxygen presents a more substantial risk to divers and the absolute partial pressure limit for recreational divers. That is important. So 1.4 and 1.6 are huge numbers. You guys want to make sure you stay at 1.4 or less when you're figuring out how much partial pressure of oxygen you want to breathe. Fair enough?
Mm-hmm.
Easy. So now, as we kind of continue this journey down the path, there are some things to be aware of. As we continue this in breathing nitrox, we can start making some decisions. Do we want to just breathe it because we want to know where the limits are, or do we want to figure out a way to be even safer? So one of the most common things that recreational divers will do is they will breathe and use an air table instead of a nitrox table, and they'll dive nitrox anyway. Now, why would you want to do that, Raw?
Because it gives you an extra around 32. If you're diving 32% oxygen, then you're going to have about an 11% safety region just added to your table on top of the already added safety margins that are in there.
Absolutely. And if I told you it was a little bit more than 11%, would you believe me?
Yes.
Okay, good. I would hope you would. Now, hopefully you guys have your cell phones out, because what I'd like you guys to do, if you wouldn't mind terribly, is pull your cell phone out for me.
Mm-hmm.
If you wouldn't mind, open up the My SSI app.
Okay.
And once you're at the My SSI app, you're going to go ahead and go to More and then Tables. Are you there yet?
Yep.
More is at the bottom.
We're there.
Okay, perfect. And once you're at the table, scroll down and you're looking for the combined air/EANX table. Go ahead and click on that. And if you wouldn't mind, just make sure you switch it over to US Imperial, because if you don't, it's going to do it in metric. Does that bring up a table for you? All right. So I like looking at this table, and here's why. As we look at the side here, if we go to 60 feet, that gives us a total bottom time of 50 minutes if we're just breathing air. Now, if you look at that same table, how much more time do we get if we're breathing 36% nitrox? The closest you're going to find is going to be 57 minutes. Or 57 feet, I'm sorry, gives you 130 minutes. So if you're breathing 36% nitrox and you decide to do a dive on air, instead of having 50 minutes of time, you get 130 minutes of time. That means if you're diving an air table, that means you're coming up 80 minutes earlier than you have to. So a little bit more than 11%, right? Are you guys seeing that? You guys are on mute. Oh, no, you're not. Are you there? Hello? Bueller? Bueller?
Hi.
What depth were we at again?
I'm going to put this on the share my screen, and we'll look at it together. So here's the cool thing.
Oh, yeah, there it is.
Right over here. So this is the table we're looking at. So if we dive on air, or if we're diving 36% nitrox, and we dive to 60 feet, if we dive the air table, it says we can only stay down for 50 minutes right here. See that? 50 minutes total. If we're diving 36% nitrox, we actually, at 57 feet, we actually have 130 minutes of available time to us, which means we're limiting ourselves to 50 minutes, which gives us an 80-minute safety margin. Does that make sense?
Yep.
See that? Okay, good. Just want to make sure we're all the same sheet of music. So as we dive nitrox, you can see really quickly that the benefits, while it's only 15%, 15 points more, or 15% more, we're getting 2.5 times the amount of time out of our dive. If we're only breathing 32% nitrox, at 63 feet, we get 70 minutes. So we get 20 minutes more on nitrox. Or we can cut our dive short by diving the air table, and we can dive only 50 minutes and give ourselves a 20-minute safety margin. And it's so you have that choice. You can absolutely dive the safety margin, or you can dive nitrox and take the full advantages if you'd like. So one of the benefits of diving nitrox is you are uptaking less nitrogen. And if you're uptaking less nitrogen, you definitely reduce your chances of getting decompression sickness quite a bit, because decompression sickness comes from what, Andrew?
It's the buildup of nitrogen in your blood tissue and body.
Exactly. It's the bubbles from nitrogen. So if I breathe less, I get less sad. Now there is a sacrifice.
How does
is diving richer better?
Yes.
Yes. Why?
Because if you're not diving with a heavy dosage of nitrogen, then you're not going to have that buildup in your tissues, and you have less chance of getting the bends from it.
Absolutely. So, but let me put it to you this way. If one Snickers bar is really good for me, and I love it, love it, love it, are 15 better?
No.
Oh, no. So there is a point. We definitely need to take into account sometimes more is not better. So just kind of keep that in mind as we go through this, that there is definitely a balance that we want to make sure we're encompassing here. So as we're kind of dealing through this, we're dealing with a lot of fun laws. And two of the laws we're going to be dealing with are going to be Henry's Law and Dalton's Law. And Henry's Law is the amount of dissolved liquid directly proportional to the it gets really boring really quickly. What it's basically trying to tell you is that in Henry's Law, the amount of gas that will dissolve in the liquid being your bloodstream, is directly proportional to the amount of partial pressure of that gas, as well as the temperature and the movement or agitation. So basically, if our heart is pumping faster, we're going to pump more nitrogen in our system, right?
Mm-hmm.
If we're breathing a higher partial pressure of nitrogen, for example, we're 33 feet and the nitrogen is 158%, we're going to be dissolving 158% equivalent of nitrogen into our bloodstream, right?
Mhm.
Mm-hmm.
That's what Henry's trying to tell you. It's more complicated than it needs to be, but that's what it's basically trying to tell you, is that the partial pressure will dissolve into your system. Now, the one thing that really is kind of interesting that we really don't get into enough is about the temperature. So one of the other things to be aware of is if you are diving cold water, then your body temperature, if you're diving 60 degrees versus 96.8, right?
Mm-hmm.
Partial pressure of that nitrogen will dissolve into your bloodstream much more quickly and the reason being is because it's dense. The denser it is, the more it'll flow into your bloodstream. Does that make sense?
Yeah.
Okay, good. I always like to check myself to make sure I'm making sense. Nikki says I don't make sense a lot, so it's okay. So, all right. So as we go through this basic idea, so Dalton's law is our basic law for the nitrox calculations that we're going to use. And it basically reads out to PG equals FG times P, which is insanely boring. But the good news is the formula is actually pretty simple. Hopefully you guys have a calculator because we're going to do a little bit of math together so we know how to do this. The good news is everything we're going to talk about tonight, there is a chart. If you were to go to that same My SSI app, and you were to go back into the table section that we showed you, you will find that there are tables for everything. There is a table for best gas mix table. There's a table for maximum operating depth. There's a table for the NOAA auction limits, the OTUs as well. So the main ones we're going to talk about right now are going to be best gas mix and maximum operating depth, or the MOD. So let's go ahead and start with the partial pressure and figuring that out. You guys ready? Do a little bit of math. So we'll get some constants going here, and I'm going to share my screen again. Hopefully you can see my screen. But Dalton's law in practical application basically says this. The oxygen we're breathing at the surface is 21% oxygen, 79% nitrogen. If we go to 33 feet seawater, we're going to talk tonight, we're going to talk everything about being at sea level, and we're going to talk everything about being in the water, in salt water. So fresh water is just a little bit different, but it's not that big a deal. So 33 feet seawater equals 2 atmospheres. So what that tells us is at 2 atmospheres, 21% oxygen is equal to 42%. We already kind of equivalent that out. 2 atmospheres is also equal to 33 feet seawater. 3 atmospheres at 21% oxygen is equal to 63%, just like you said. And 3 atmospheres is equal to 66 feet seawater. Now, nitrogen does this exact same thing. So 2 atmospheres of oxygen or nitrogen is at 79% equals 158%. Now, again, safety note, oxygen becomes toxic at 1.6. So the working load for oxygen for safety is 1.4 for recreational divers. Now, on that same note, nitrogen begins to become narcotic at 2.37 or 237%, and nitrogen becomes unsafe at 395%. Now, nitrogen narcosis will be equal to 1 martini on an empty stomach at 100 feet, and it will increase exponentially after there. Make sense?
Mm-hmm.
And we will absolutely get into nitrogen narcosis here in just a moment. But the fun math. So our formula for figuring out the best mix for nitrox. So Ron, Andrew, and Caleb, we all decided to go out to Florida. We're going to dive the Lady Luck. Lady Luck is one of my favorite dives in the world. It's a 385-foot barge that was sunk in it, and the deck is at 115 feet. Love this wreck. Love, love, love. It's just a fun wreck. So if the diver, wanting to make sure that he stays below 1.4 working load, he wants to know what is the best mix. What's the exact percentage of nitrox he wants to do to get down to 115 feet? Make sense?
Mm-hmm.
So what is the best mix for this dive? So here's how we're going to figure that out, you guys. We're going to take 115 feet. We're going to divide that by the feet seawater. Now, if there's the next thing to tattoo on your forehead is that you always want to make sure you're either adding or subtracting 1. And now the one is the surface atmosphere that you need to either add or subtract from every formula. There's always going to be a one added for the surface atmosphere. So 115 feet divided by 33 feet seawater equals 3.48 plus 1 equals an actual atmospheric depth of 4.48. Now, easy enough. You take that 1.4 that we've talked about, and you've just written on Andrew's forehead, and we divide that by the 4.48 equals 31% nitrox. Now, let's go over and check ourselves. Remember, we're diving to 115 feet. We go to our chart that's right on the SSI app. Here's 115 feet, 31% nitrox. Apparently, I got my math right.
Mm-hmm.
So now, do you guys have a pencil and paper?
Yeah.
Oh, no.
1 second.
All right. So if you have a pencil and paper, I'm going to stop the share of my screen for a moment, and I've got some test questions for you. So, Ra, if I wanted to go to 120 feet seawater, what would be the best blend for me? Now, remember, we're going to divide 120 divided by 33 plus 1. What does that work out to?
Okay. Oh, my thing isn't working. Oh, thank you. All right. 20, 33. Why would it work? Thank you.
Let me make it easier. I'll put it on the screen.
Okay, so 4.63, and then you go ahead and
That's exactly right. So
The 1.4.
yeah, 4 divided by
463.
4.63 equals
30%.
30%.
I'm sorry, what'd you come up with?
30%.
Perfect. Let's check you. 120 is 30%. Good job. Andrew, are you ready for yours?
Yes.
All righty. If you wanted to go to 90 feet, what is your partial pressure?
3.72.
4. 30. Well, I'd round up and say 38%.
Let's take a look. So 90 feet is not on my chart. So let's do the math on it. I'm going to actually have to do the math because it's not on this chart for some reason.
37.6.
90 divided by 33 plus 1 equals, so in this case, x equals 4.7272, which means this is 4.7272. So 1.4 divided by 4.7272 equals there you go. Is that what you came up with?
No.
What was your answer?
I had 37.37.
Little high.
Yes.
Now, do you see how we came up with the answer? Let's just check our math. 90 divided by 33 plus. Oh, wait a minute. My math was wrong. I apologize. 90 divided by 33. For some reason, I missed somewhere. Is, I'm glad I'm checking my answer. 3. I must have fat fingered. So that's 3. So 1.4 divided by 3.7272 equals, Andrew, it equals, the instructor was wrong. Andrew was right.
Yay.
Hey, there we go. Sorry, I fat fingered the calculator. So I apologize. Good job. That is the process to figure out the partial pressure of nitrogen. Or not, sorry, partial pressure, but the best blend for your dive. So this is how if you go on a dive and you know where you're going to dive to, you get the research and you say, oh, I'm diving 115 feet. You can simply go to the chart or you can do the math. honestly, the math is so easy. I never look at the chart. I've not once been on a dive site and said, hey, I want this or that or the other. So that's how you figure it out. Super simple. Now, the other side of this, and do you guys now see Dalton's Law Practical Application Mod? Okay, good. I just want to make sure. So the other side of this is we have to have a maximum operating depth. How deep can we go? Now, remember, we want to make sure we're staying within the working load, 1.4. That's an important number when figuring out the maximum depth we can dive a gas. So we've shown up at a dive site and they've given us 32% or 32%, right? How deep can we go? So simple enough. In this particular case, we're going to say 1.4 divided by the partial pressure of the cylinder minus 1 equals the ATA times 33 feet. So in this particular case, a diver wants to dive 40% nitrox. I loaded your tanks up for tomorrow at 40%. How do we figure that out? 1.4 divided by 0.40 equals 3.5. 3.5 minus 1, remember we always have to either subtract or add for the surface, equals 2.5. 2.5 times 33 feet equals 82.5 feet. We come over here, 40%, 40%, 40%, 83 feet. It rounded up. Pretty easy.
Yeah.
Okay.
So let's go ahead and do some actual math. Guys?
So that would be a gas mix of nitrox 40 then, right?
Correct.
Okay.
Andrew, you showed up at a dive site and they gave you 32% nitrox. How do we know how deep we can dive on 32% nitrox?
The table, or we do 1.4 divided by 32
minus 1.
minus 1.
Then you do minus 1, yeah?
Correct.
0.43. 43 minus 1. And then you divide that by 33 feet.
Multiply.
Multiply by. Okay.
Yep.
What a negative number. I think I did it.
Yeah.
So as we look at it, it should be 1.4 divided by 0.32.
Okay, that makes more sense.
1.4 divided by
32, which
Oh, that makes more. 0.32. 0.32. Our bad.
equals 3375.
5.32. And then you do plus 1. No, minus 1.
minus 1.
Sure, 3.375.
Correct.
Times 33. 375 times 33.
Times 30. And it's
111.
111.375.
Exactly right. That is all there is to it. Not very complicated, is it, guys?
No, that makes sense.
It's pretty basic stuff. Now, the good news is now you know how to do the math. But if you should need, before you go on a dive trip, what it would, if it were up to me and you're just new at this, let's see. There we go. I would take a screenshot of this and I'd have it on my phone.
Yeah.
Screensaver.
Absolutely. And we're going to get into why that's important as well.
If you don't have any internet service.
Well, yeah, but why you should always know how to figure out your mod. Easy enough.
Because sometimes other people make mistakes, so it's good to check them.
Absolutely. So fun trivia for you. I was on a dive trip about a year and a half ago. Nikki and I got to Florida just after a hurricane. We've been diving caves all week and we decided we wanted to do some ocean diving. Only found one boat that was going out that we could get on. They were doing some pretty easy 60, 65, 70-foot reef dives, and we ordered up. We wanted nitrox. We couldn't order the blend we wanted, but we could order nitrox. So as we got there, they were putting our tanks on. I says, wait, I need to analyze that. And the dive master on the boat said, well, I analyzed it. And I says, well, that's great, but I need to analyze it. And he looked at me and says, but I'm a retired firefighter. I said, thanks for your service, but I need to analyze my tank. He says, you don't trust me? I says, nothing for nothing, but I've known you for about a minute and a half now. No, I don't trust you. I need to analyze my tank. And he says, but I analyzed it. I'm a retired firefighter. I said, thank you for your service. Where's your analyzer? He was very, very upset with this, but in the end, when he got his analyzer, we analyzed our own tanks. And while he was actually fairly correct on it, I still wanted to see. I don't trust anybody, not even Nikki, to analyze my tanks. And no offense, she doesn't trust me either to analyze her tanks. She analyzes hers, I analyze mine, and that's how it is. People make mistakes, and you, in the end, you were responsible for your dive. Make sense?
Yep.
Yes.
Now, as we're going through this process, be aware that nitrox will help you avoid things like being narked as well. So as you got to go through this process, you're going to avoid nitrogen narcosis, which is a high buildup of nitrogen in your system. And so that's a kind of a great thing. And because you guys are only certified to 60 feet, it's not something that you're going to have to worry about. So keeping with the law of what do the students need to know and when do they need to know it, you don't need to go into nitrogen narcosis at all at this point. And so we're going to skip that because you don't need to know it right now. It's not important. But let's get into the effects of oxygen on the diver. So there's different kinds of effects that we certainly deal with. Hypoxia or anoxia is what? Rob, what does it mean if I'm hypoxic?
When your oxygen blood level drops too low for you to function properly.
That's exactly right. So what does it look like when I get hypoxic?
Dizzy. Usually you'll have, in some patients, darting eyes. Other ones will just kind of glaze over, and then lots of gasping. And then if it drops any lower than that, they usually just pass out.
Absolutely. So that's pretty common. Nausea, disorientation, vertigo, narrowing of vision, ringing of the ears. Those are also symptoms to be aware as well. With this course, we're not worried as much about hypoxia as we are about hyperoxia. Now, what is hyperoxia?
Where you're just basically too full of oxygen or exposed to too much oxygen, and then you start getting funky because your blood molecules are generally rushing around too quickly.
Absolutely. So there's two types of hyperoxia to deal with. There's pulmonary oxygen toxicity. That's the first problem. And then there's central nervous system toxicity. Now, the first one, this was studied. Do you know this? When was the first studies of hypoxia or hyperoxia done for pulmonary oxygen toxicity? Do you know?
I don't know that one.
1899.
Oh, wow.
A long time ago. It's pretty
Makes
interesting. So Dr. J. Lorraine Smith first described the toxic effects of oxygen in the lungs in 1899 while studying rats. Now, he noted that the severity of the effects increased with a partial pressure and that the effects were largely reversible. Now, the toxic effects of oxygen at partial pressures between 0.45 and 1.6 are primarily in the lung system. They're pulmonary based. The toxic effects of the partial pressure of oxygen over 1.6 are primarily in the brain, if you have one. Just kidding. I have met some divers that I'm quite sure could never get central nervous system toxicity because they don't have a brain. But that's just my opinion. It's not a medical fact. Now, what we discovered with this is the earliest signs of pulmonary or lung oxygen toxicity begin with a mild irritation in the trachea and the throat. And is made worse by deeper breathing. Now, this is followed by a cough that develops next. Maybe yesterday I had some pulmonary oxygen toxicity. Maybe that's why I was coughing. Just kidding. That's not why it was happening. Cough I can't get rid of. But that is absolutely a sign of pulmonary oxygen toxicity. Now, what we discover is as it gets more severe, this is followed by severe irritation and cough until breathing becomes quite painful and a cough becomes uncontrollable. Now, if that exposure to oxygen is continued, the person's going to notice a tightness in the chest, difficulty breathing, and shortness of breath. And if the exposure continues long enough, the person will die from literally lack of oxygen. What's happening is the progressive damage to the lungs makes it impossible for the oxygen to get to the blood as it passes through the lungs. It's literally overwhelming the hemoglobin barrier in the lung system to the point that it shuts down. Pretty wild. So that's what we deal with when we're starting to talk about pulmonary oxygen toxicity. But here's where it gets interesting, I think. And while we talk about this, it's good to know that the time and onset of symptoms is highly variable. Now, most individuals can tolerate between 12 and 16 hours of pure oxygen at 100%. 12 to 16 hours. So your average patient, 100% oxygen for 12 to 16 hours is all you really should before we start having problems. 8 to 14 hours if you're breathing 150% oxygen, for example, in a hyperbaric chamber, or 3 to 6 hours at 200% oxygen before developing mild symptoms. Now, there's several ways to track pulmonary oxygen toxicity, but the most sensitive and most accurate is really the development of symptoms, coughing, tightness of the chest, things like that. Now, a second technique is to monitor the vital capacity. Now, vital capacity is the amount of air that can be moved in one large breath, right? Now, decreases with the increased pulmonary oxygen. The volume of vital capacity decreases with increased pulmonary toxicity. So basically, as you get more pulmonary toxic, you can't move as much air with one breath. Now, a reduction of about 2% of vital capacity correlates with mild symptoms, and a reduction of 10% or more correlates with symptoms so severe that most individuals will not voluntarily continue to breathe. They have to be intubated, in other words. Now, these effects are completely reversible, and no permanent lung damage generally occurs, but it could take 2 to 4 weeks to completely heal. Now, as we move over to the other side, when we start getting that high dose of partial pressure of oxygen for long periods of time, the first thing we need to worry about is the signs and symptoms of that are remembered by the acronym CONVENTED. Now, CONVENTED stands for convulsions like grand mal seizures that are usually without warning, vision like tunnel vision or any other change in the visual field, ringing of the ears like tinnitus, nausea, mild to severe or continuous or even intermittent, twitching. Usually the twitching happens in the facial muscles, which makes perfect sense if it's central nervous system toxicity. And it's one of the most frequent symptoms that we deal with in central nervous system toxicity. Now, other things to be aware of, the eye for irritability, behavior, or personality changes. I'm irritable all the time, so it's hard to tell that. Maybe other people get really irritable, and they're not, so if Raw gets really irritable and she punches you again, I know that's why you didn't make it Wednesday, by the way. I know you said something smart, she just smacked you, and it's okay. You can give me the safe word of pizza, and I'll know that you're an abused man. It's okay. Just whisper it to me tomorrow, okay? Just kidding. Last symptom to be worried about with CNS toxicity is going to be dizziness, vertigo, or disorientation. So now, Andrew, of these symptoms that we just talked about, what do you think you would notice in Raw on a dive?
Probably.
Yeah, I'm not an easy target for this question. Both of us.
I put it on screen. So, So, Andrew, do you think you'd notice convulsions?
Yes.
There we go.
Absolutely. If she was staggering wildly on the deck, do you think you'd notice that?
Yes.
If she reached over and just slapped the snot out of you, would you notice that?
Maybe.
You would notice if she slapped the snot out of you?
Maybe. I don't know. It might be on the bottom of the boat. Yeah, I guess it'd be like convulsions. I wouldn't really necessarily notice her vision or ears. Nausea, I probably could notice. Twitching, irritability, dizziness.
Absolutely. Now, diving is a very, very self-aware sport, guys. How you feel going in the water is how you should feel coming out of the water. So one of the things I do during diving is I make sure to take a mental assessment as I'm diving along. I do basic math in my head. How long will it take me to get to the surface? How fast am I going through the air? What's my air consumption rate? So I ask myself mental acuity questions. And I also do 1, 2, 3, 4, 4, 3, 2, 1. How's my dexterity, right? Am I able to do simple tests, right? And I do that on a regular basis to check myself. And I check myself on the dive boat. But you also need to watch your partner. Now, Nikki and I have done a lot of dives together, and I get a very clear idea where Nikki's at. When Nikki gets upset, I batten down the hatches and I bow before my wife, and I'm so sorry, because that's very, very unusual. It just doesn't happen. So be aware and watch your partner for things as well. Is she acting differently than normal? Now, it could be differently because she just saw an octopus and played with an octopus and grabbed onto her leg and played with it for 20 minutes, and she's excessively giddy. Maybe that's the reason, but it's certainly something to be aware of. So as you got to go through this process, make sure you're not only aware of yourself, but also be aware of your partner, what they're going through as well. Does that make sense?
Yes.
Mm-hmm.
All right. So as we got to go through this, be super aware. So questions for you today. As you dive deeper, the narcotic effect of nitrogen gets
Stronger.
More
stronger.
likely.
I'm going to flip my screen back on for you guys. There you go. Can you see the quiz time?
Mm-hmm.
Perfect. Stronger. So next
Greater.
question. Which of the following is not a symptom of decompression sickness?
Weakness, extreme fatigue, cyanosis, bluish skin color, tingling or numbness in the extremities.
I believe it's tingling.
I believe it's cyanosis.
It is
Bluish.
cyanosis.
Yeah, because if you're getting decompression, that's the bends. The first thing you're gonna have is the tingling, and then it's gonna move to like, oh my god, what's killing me?
Okay.
So yes, cyanosis is exactly right. Because cyanosis is generally a sign of one of two things. What are they, Raw?
Either you're getting hypothermia or you lack oxygen
Exactly. Good job.
because you blew in the face.
Even if a diver suffers from decompression sickness in a remote location, you should never.
Oh, you were waiting for us to finish that sentence.
Recompress the diver underwater.
Exactly. That's exactly why, Andrew.
What is it? There's never everything that we want to do medically is easier to do on land than it is in the water.
Absolutely.
And
That's
you might endangering yourself trying to take a seething person back under the water.
Mm-hmm.
You bet.
That's
And besides, using the AED underwater is just all kinds of fun, right?
Just grab one of the electric eels.
Absolutely. Now, Raw, for you, this is a fun one just to say. Hypoxia is by far the most common form of hypoxia. This condition is where?
The partial pressure of oxygen in the arterial blood is too low. Nitrogen, partial pressure of oxygen in the arterial blood is too high. No, it's the first one. Partial pressure of oxygen in the arterial blood is too low.
Ding, ding, ding. Exactly right. All right. Now, I asked you guys to write a number down for me earlier. When oxygen pressure in the body drops below the partial pressure of 0.17 ATA, mild symptoms of hypoxia occur. Blackout and death may occur if the partial pressure drops below
0.10.
0.10 is exactly right. All right. And finally, a possible source of contaminated air in a scuba cylinder is?
It hasn't uploaded or switched.
Oh, it didn't switch? I'm so sorry.
But rust and a whole bunch of others.
Let me just reshare. Just take me a second here. There you go.
Yeah, improperly located intake on air compressor, maintained air, oil vapors, all of them.
Mm-hmm.
All of them. So one of the things you'll notice is when you get on a dive site in wherever in a third world country, more accurately, a lot of times they'll be using diesel compressors, and you'll see them put the exhaust too close to the intake. It happens. If your air smells like anything, please, please, please do not breathe it. Even if it smells like candy canes, don't breathe the air.
Mm-hmm.
Well, now, as we talked a little bit earlier, we talked about Henry's law. And Henry's law is the amount of gas which dissolves in a liquid is proportional to the partial pressure of the gas based upon agitation and temperature, right? And so as we got to go through this, to understand this, how this works is as we breathe in and we're breathing in a specific partial pressure of oxygen or air, right? And it goes into the lung, down the trachea, into the lungs, into the alveolar. And now, how many alveolar do we have in our lungs, Andrew?
Millions.
300 million to be exact.
Okay.
Well, about. It would be exact. It'd be about 300 million. We have 300,118,912 I'm just kidding. I don't know. Nobody knows, right?
Yeah.
No, and nobody counts them, right? But what it does is once it hits the alveolar, it goes into the bloodstream and it carries that gas, that partial pressure of air and nitrogen out into our tissue. Now, as we ascend in the water column, that partial pressure has to be relieved. It comes out of the tissue in the form of silent bubbles. And then eventually it brings back through our heart into our lungs and we exhale it. That's what's going on with the partial pressure. We breathe it in, we breathe it out. We're exhaling the whole process. Make sense, guys?
Uh-huh.
Now, in the early 1900s, J.S. Haldane decided that he had to figure out what this looked like and how we determine how the gas model is working, because he wanted to be able to figure out how we're stopping the bends. What was happening is in the late 1800s, when they were building the Brooklyn Bridge, they were sending divers down in these large bells called caissons. And they were sending them to 150, 200 feet, 300 feet down and having them work. And as they're doing this work, they'd come back up. And what was happening is the nitrogen bubbles were coming out so fast that they were getting the bends. And so he wanted to figure out what this looked like and how do we stop this process. And so he started coming up with some basic models of how this works. And he came up with an idea that when we get past a double partial pressure, that we need to stop and start slowing our ascents down considerably. And he's the one that came up with 33 feet per minute through the process and said that once it gets to double partial pressure, we are now at the risk of decompression sickness. Make sense?
Mm-hmm.
So through that process, we realized that we needed to, in recreational diving, we needed to add a safety stop. We needed to impose time and slow down our ascent so that we were not off-gassing the nitrogen as quickly, but we also needed to stop at a point to allow the nitrogen to slowly come out of our system so that we were more safe. And so as we came up to the safety stop idea, we determined that 3 to 5 minutes was the most appropriate at 20 feet. And if we stopped at 20 feet and allowed this partial pressure of nitrogen to come out, we increased our safety margin considerably. Now, as we kind of looked at this, the basic idea is, and let's see if my screen will share. Do you guys see my red and green screen?
Yes.
Yep.
Fantastic. It's working. So what we discovered is that there's the safety margin between the actual M value, and M value is the maximum value or maximum amount of gas a tissue compartment can hold. It's much like a balloon. There's a maximum amount of air you can put into a balloon before it pops, right?
Mm-hmm.
So the M value is where things get bad and things pop, right? So there's a margin between them, but the problem is that margin is different on every day in every person. So how you process nitrogen and what your M value is for your tissue compartments is different than mine. Andrew, yours is different. Caleb's is different than all three of ours. And it depends on if I had a good night's rest, if I drank enough water, if I was fighting with the dog, whatever it was, that value can change. Now, what we discovered with this as well is that if we take less time at safety stops, less deco, if you will, and ascend faster, we increase our risk dramatically from changing those bubbles from silent bubbles to bubble seeds to symptomatic bubbles. So faster and less decompression stops or less safety stops increases our risk dramatically. Now, if we increase our safety stop time and we decrease our ascent time, we allow more bubbles to come out of our system, and we get to the point where we have less risk. So from the slide, I want you to take away a couple of things. First, dive tables and safety stops are how we manage the size of the bubbles in our bloodstream. The second is safety stops assist in the reduction of the size of the bubbles. Number 3 is there's no clear line between good and bad, and every diver is different in the way their body manages the size of the bubbles and reduces them. So guys, please do a safety stop. Simple enough?
Mm-hmm.
Now, do you guys see the blue and red and yellow chart in front of you?
Yes.
Fantastic. So interestingly enough, there was a recent study by International Training, and they took 3 different kinds of divers out, and they were all diving to 120 feet for 25 minutes, diving nitrox. Diver group 1 did a direct ascent to the surface from 120 feet without a safety stop. Now, what they determined was that about 16, 17 minutes after the dive, they were at about 115,000 bubbles per cubic liter. Okay. It's a lot of freaking bubbles.
Yep.
Now, over the course of 2 hours, you can see they reduce. In about the 45 minute, they're at 60. Then at 60 minutes, they're at about 24. And finally, at 2 hours, they're just below. They're like 18 to 19,000. Now, diver group number 2, they stopped at 10 feet for 2 minutes. Is that a pretty good size reduction in bubbles?
Yes.
Absolutely. Just by doing a basic safety stop, look how safe they are. By the end of 2 hours, they're down at 6,000 bubbles per cubic liter. Now, there's a third group here. This is the group that I'd like you guys to think about being in. They stopped at 20 feet for 1 minute and 10 feet for 4 minutes. Now, when they came to the surface at 15 minutes, they were nice and low at about 7,000 to 8,000 bubbles per cubic liter. And at 42 minutes, they were at 0. 0 bubbles. Are they safer or less safe?
Safer.
Safe.
Absolutely. So there's a couple takeaways from this that I'd like you guys to take away. The first one is a safety stop reduces bubbles. The second one, a longer safety stop reduces more bubbles than a shorter one. And a 5-minute safety stop during repetitive dives increases the safety margin considerably. Takeaway, do a safety stop, please.
And that's something you can still explore at that elevation. You just have to, just stopping at that elevation is nice, right?
Absolutely. In fact, one of the things tomorrow after my dives with you, I'm taking a couple of extended range tech students out. And part of our dive plan for tomorrow is going to be exploring and taking time. We're going to be at, I'm pulling up their dive plan. Let's see, we're going to be at 40 feet for 5 minutes. We're going to be at 30 feet for 10 minutes. And we're going to be at 20 feet for 15 minutes.
Okay.
So we're going to be 30 minutes. We're going to be 30 minutes at 40 feet or shallower for our dive. So as we go through this process, we're going to spend time at shallower enjoying the time.
Nice.
So absolutely, you can take that time. So simple enough. Now, one of the biggest things I can tell you about diving to add additional safety is the idea of adding a dive computer. Do you guys see the dive computer on my screen?
Mm-hmm.
Fantastic. Now, the history of dive computers is actually pretty interesting. Back in the 70s, the Navy went to the Naval Experimental Diving Unit at Scripps Institute, and they said, hey, our divers are getting bent. We need to figure a way to make them safer. How do we do that? We want to add a computer so that they have a tactical advantage over the enemy so that they're able to stay down long enough to be able to accomplish that task and know when to come up so they're safe. So the first dive computers were actually classified top secret. So their intended use was to be able to monitor the amount of nitrogen in your system based upon your depth and your time. Now, modern dive computers have come a long way, and they've added quite a few cool features. For example, this particular dive computer will monitor the amount of gas in your tank. As you can see, this particular dive computer shows you have 1,810 PSI in your tank. How handy is that to have that on your wrist?
Very handy.
Absolutely. The other thing it'll tell you is over on this left-hand side, it has an ascent meter. Green means go, that you're fine. Yellow means slow down. Red means stop. Raw, how handy would that be for doing an ascent to the surface?
Exceedingly useful.
Absolutely. And then finally, it has a no decompression limit. So as you look at this, you're able to say, oh, wait a minute, I've got 36 minutes of time before I have to surface. Pretty handy.
Mm-hmm.
And then just for fun, it also has a temperature gauge on it. So it'll tell you the temperature of the water, the depth you're at, how much gas, a lot of information on your computer. Now, they do have a few limitations. Battery life is certainly one thing. You do have to recharge them to make sure that they work. But they're also can be limited by the temperature of the water. So if you're diving really cold, you need to make sure you're adding additional conservativeness to your dives to make sure that you are safe. Make sense?
Mm-hmm.
Or if you're diving altitude. All right, let's see. Now, one of the things to be aware of as well is as you dive all dive computers are designed to dive your deepest dive first and then go shallower and shallower and shallower. If you try to take your dive computer in reverse, it does not like that, and it won't be happy with you. And it won't give you an accurate reading of what's going on. Make sense?
Yes.
Mm-hmm.
Now, to get down to the meat and potatoes, we talked about how to analyze the tanks. We talked about a few other things. How do we actually analyze the tanks? And what does that look like? So the good news is on Sunday, I will have an analyzer at the dive site that you can use, and we will analyze your tanks ahead of time. Oop, there we go. So simple enough. The first thing we do is we calibrate the analyzer to what we're using. We want to make sure that it's reading correctly, and all analyzers calibrate. So the first thing we're going to do is, before we do anything, we're going to calibrate to make sure that it's reading 21%. 21% what we're breathing, right?
Just the atmospheric air.
Exactly. Once we've done that, then what we're going to do is we're going to crack our cylinder just slightly. We're going to put the analyzer over the nozzle to make sure that it's able to breathe what we're breathing. And if we give it enough time with a gentle, very low flow, you'll see the numbers will move, and it'll give you a new percentage of what is actually in your blend. Make sense?
Yeah.
Now, as we go through this process, there's a few things we want to make sure we do. We want to make sure that we always, always, always mark our tanks appropriately. So as we mark our tanks, we want to make sure we do a few things. And I do not encourage using a tag over the top of your tank. You want to put a piece of duct tape on both the front and the back side by the valve, as well as the bottom of your tank right over here as well. And on this sticker, you're going to need to put a few things. The first one is going to be, what is the partial pressure of the nitrox that you're breathing? What is the maximum operating depth, and what did you use as your partial pressure point? When did you do it? And your initials or your name to let us know who did it. It's important information, isn't it?
Mm-hmm.
Absolutely. So we want to make sure that as we go through the process that we're doing that. Make sure we always, after we analyze, we mark our tanks. Now, as we look at our tanks, we want to make sure that we're using tanks that have been O2 cleaned and are prepared for nitrox. Because one of the things that they will do in cleaning your tanks is they will make sure they change out the rings, and they'll make sure that they clean the inside of the tank so it's prepared for a higher percentage of oxygen.
Is
Now,
the ring a different type of any, or is it the same kind of like?
It is
gasket?
a different.
Okay.
It's generally they're made out of Viton, and they're generally brown. The thing we have to realize is with oxygen, or a higher percentage of oxygen, is it will cause the different parts and pieces of our regulators and our rings to erode, because pure oxygen actually has an erosion factor to it. So that's why we have Rule 40. So you guys are going to deal with Rule 40, and you're limited to 40% or less. What you'll find is most scuba gear is designed to be able to be used with up to 40% nitrox.
Okay. So
most regulators are pre-designed to do that. And so we call it Rule 40 as we go through this process. And that's why we have, your guys are always certified to 40%. But we want to make sure we see that it's marked as a nitrox tank and that it's been O2 cleaned. It needs to be checked once a year. So as we look at it, we also want to make sure we look at the visual inspection sticker that it says it's been analyzed within and cleaned within the last year. Make sense?
Yes.
Be aware that with higher blends of oxygen, we deal with oxidization and wear. We also increase the risk of explosion and fire, because we all know that fire loves oxygen, right? So just be aware that as we handle this, we definitely want to be careful. We are dealing with a more higher fire.
Flammable.
Thank you. A higher level of fire risk with us as well. So just be very careful as you go through this process as well. Now, as we go through this process, just be careful. Make sure you mark your tanks. Make sure you know how to do the mod and what blend you have, and check things out very carefully. What questions do you guys have?
I'm good. It was all pretty straightforward, but
general question, I guess, is because we have nitrogen buildup when we're scuba diving, but we're breathing the same air that we breathe when we're not underwater. Is it just the pressure of the water that's causing the nitrogen buildup in our blood and everything?
It is. As we build up pressure, it increases the partial pressure of what we're breathing. As we ascend in the water column, that pressure is released, and that previous partial pressure, the higher partial pressure of the nitrox, has to come out of our system. Because what will happen is, if you go down to 33 feet and you're breathing 158% nitrogen, your cell tissues are loading up with 158% nitrogen. As you ascend, that partial pressure is becoming less, and it has to equalize with the ambient pressure around you. So that higher partial pressure of nitrogen is coming out of your system.
Okay.
Makes sense?
Yes.
Easy enough.
I had another question as well, just based off some of the reading that I was doing. And I was just wondering if you had any experience with this. So apparently, if you can do an infrared sauna before you go scuba diving, it can actually help eliminate the amount of bubbles that you will experience post dive.
I have no experience with using infrared sauna at all. I'm not sure what the effects or the benefits of that would be.
Basically, it's just going to make your blood move faster and at a little bit of a, like, less than a quarter of a degree warmer is basically what you'll remain at for the next 24 hours when you use an infrared sauna. So I was just wondering if you had any,
I don't have
just based
experience.
off your experience with.
Here's the thing to remember about
faster.
diving. Water wicks body temperature away 25 times faster than air. So when you get in the water, you're going to be wicking the temperature away. So your body's going to be cooling very quickly, 25 times faster than air.
Okay.
I just figured out with you saying that how it would work, because based off the law that you were telling us, where it's just like the cooler the water temperature is, the faster it's going to absorb into you.
Mm-hmm.
The Hunt's law is what you were telling us it was called, or Henry's, yeah, where the amount of air parts per air dispersed. So if your blood temperature was warmer before you ever started that process, then you would have just a tiny bit of an advantage. Not much, but a little bit.
It would slow the absorption, but the other challenge is you got to remember the air is coming in colder. And so if the air is coming in colder, it's not the blood temperature, but it's the temperature of the gas. So if the gas is coming in colder, it's not the temperature of the air or the blood, the liquid. It's the temperature of the gas. So if the gas is coming in at 31 degrees, it's going to come in, it's dissolve into the bloodstream faster than if it was at 50 degrees. So it's got to remember, it's the gas that you're
tank pressure.
So your blood temperature really wouldn't have much to do here. It's going to dissolve based upon the temperature of the gas and the agitation of the liquid. So how fast your heart's beating and what the temperature of the gas is, as well as the partial pressure.
So it's not body temp as much as it is gas temperature.
Oh, exactly. I see. So that's good to know, because that means that even as a guy, because guys generally run warmer than women, then that means you guys don't even have that advantage over us. We're all equal.
You should absolutely finish with a lot more gas than everybody in the pool. I would really compete against you, but at some point, with enough experience, you'll beat me. I go through I've got a very, very low sac rate, but I also I dive a lot and I practice a lot. So it just is what it is. So I generally don't go through much gas.
Okay. Is there any questions that you would be asking in our position?
The big ones to be aware. So as I teach these classes, I go by a simple rule of what do you need to know and when do you need to know it. What you need to know is how to figure out your maximum operating depth. We talked about that. How to figure out your the best blend of gas, and how to analyze the tank and how to mark the tank. So those will be the 4 things that you need to take away from this class that are extremely important.
Gotcha. Okay. Well, I'm good on all of that. You good? Okay. Thank you so much. We're good.
In this recording.